be, excuse me, the first one will be presented by Alexander Ryota Keeley. And the title of that will be The Impact of Climate Change on Supply and Demand for Electricity, Power and Wholesale Electricity Prices in Germany. The second presentation will be presented by Theresa Luigs, and the title is The Relevance of Proximity and Workplace Experiences for the Support of Power Plants. And finally, the first presentation will be presented by Camille Cany, and the title will be The Impact of High Penetration Variables RES in the European Power System for 2050. Just to confirm that all 3 speakers are present. Is that the case?
Yes. Yep.
Yeah. Yes.
Okay, we have Camille, we have
Hello.
Alex is here.
We have Alex and we have Theresa. Yep. Okay. So just to note, we have in total now a little bit less than 1 hour 45 minutes for this session. So given that we have only 3 speakers, we can allow at least approximately 20 minutes for the presentation, and at least plus 5 minutes for the discussion. But I will be keeping an eye on the clock and can remind you if this goes too much over time. So without further delay, I would like to give the floor to Alexander to present his paper.
Thank you, Dr. Spodniak, for the introduction. Do you see my slides? Okay.
Yes, we can.
Yes.
So the title of our presentation is The Impact of Climate Change on the Supply and Demand for Electricity Power and Wholesale Prices for Electricity in Germany. And to give a background, increasing renewable energy have increasing impact on demand and also supply market in recent years. And for example, in our previous work, we have focused on German electricity market. And we have seen that renewable energy penetration has a merit order effect, which is the phenomenon that low merit cost of renewable energy will decrease the wholesale market electricity price. Another point is that climate change effect is becoming more serious, and weather conditions critically relate to electricity demand and also a generation from renewable energy sources. And rapid changes of weather condition critically affect the electricity market. For example, in the next slide, as we show, weather condition significantly affected Japanese wholesale market electricity prices. And as you see in the as you see the spike here, this spike occurred during the January late 2020, and this occurred because of a sudden drop in the temperature. And usually consumer price of electricity is about 20 cents per kilowatt hour in Japan, but we recorded a highest spot wholesale price in 2021, which was about $2.5 per kilowatt hour. So the impact of climate on electricity demand is really massive. However, previous studies did not reveal weather effect for both sides, supply and demand. Another example of how weather condition is important and solar generation, wind generation is important is shown by this graph. And this is the historical price of German electricity market. And we can see that there's a spike drop in some places, which is driven by a large scale generation by wind and solar occurring at the same time. So we need to look at these change in generation and also load and how they affect the electricity price overall. So the purpose of this study first is to reveal the weather condition effect for supply and demand with electricity. And going into detail, How much effect each weather factor has on supply and demand of electricity is the first question. And how much does change of weather condition affect the wholesale electricity price is the second point. And we evaluate the detailed effect of the weather condition for electricity market. To do so, we have decided to employ structural equation modeling, considering the complexity of the interaction between different variables, because we wanted to look at indirect effect and also direct effect. So we employ structural equation modeling here. And the main variables are temperature and radiation, wind speed, and solar generation, wind generation, load, and price. And we also add some year, month, and daily, week, and month variables, dummy variables. These are the data source. And we look at German at the grid level, and we use 282 grids in German. And we calculated average temperature, wind speed, and solar radiation every 3 hours in Germany. So since we only had data for 3 hours, while we had 1 hour hourly data for generation and load and electricity market price, we wanted to make it an hourly analysis. So for the data matching, we hypothesized that weather condition does not change between 3 hours that much. So then we set up the dataset every hour in German. This is the summary statistics. And this is the correlation between each variable. And I'll move on to the results. So estimation results, we can see that first and most importantly on price, load and solar and wind, they are all significantly affecting the price. And as following the theory of merit order effect, solar and wind, the increase in generation of solar and increase in generation of wind will actually decrease the price of wholesale market electricity price. And increase in load will increase the market electricity price. And these are showing the other interactions between different variables: temperature to load, radiation to temperature, and radiation to solar, wind speed to wind. To show this in structural equation modeling diagram, it looks like this. And we can see that weather conditions such as radiation, temperature, they have significant effect on load, on demand side, through radiation to temperature to load. And also they have significant effect on generation, supply side, radiation to solar and wind speed to wind. And summing up, it goes to the decreasing effect of price from wind and decreasing effect of solar to price from solar to price, and increasing effect from load to price. So based on these results, weather conditions change critically affect supply and demand side of electricity. That's the primary finding of this study. And this increases of average temperature decrease total load of electricity, especially in terms of Germany. In the context of Germany, increase of average temperature could decrease total load of electricity because electricity demand of winter season decline especially. So suppose that if 1.5 degrees increase happens in future, about 81 gigawatt demand decrease in every hour occur. And this will lead to electricity price decrease of around 0.09 cent per megawatt hour every hour. And as we saw in previous study, we found the similar finding of the effect of wind and solar. Both wind speed and solar radiation decrease electricity price indirectly channeled through wind generation and solar generation. And this is in line with the theory of merit order effect of renewable energy. And policy implication from here is that market price fluctuation not only occurs from change in load and generation, but we need to look at something that's changing these load and generation, and that is weather condition. So climate change causes rapid and uncertain change of weather condition, which means that in the future energy management system, we need to care about weather conditions change more. And also this one leads to technological choice too. Climate change effect is really different in each region. So this time we investigated the case of Germany, but in other cases with different weather conditions, the result could be different. So we need to care about the weather conditions affecting specific regional energy management. And now we are further conducting analysis of Germany by a grid level analysis and try to look into how different effect renewable energy would have in different districts of Germany. And there's some limitation in the future study and discussion. So as I said, each region has a different potential weather effect. So we need to review more detailed effect of weather condition change in specific region, for example, at the state level. And some of the improvements that could be made to do this is this time we omitted supply side factors such as availability ratio of non-renewable energy electricity generator. And we also need to confirm the robustness of relationship between the weather variables and other factors. Thank you.
Thank you, Alex, very much for your interesting presentation. So I would definitely have a couple of questions. If you want, you can still keep the slides open if we want to quickly revisit some things, if I didn't catch everything. But firstly, I wanted to maybe ask about the title. So title talks about the climate change impact on the supply and demand. And then I was wondering, then often in your presentation, the paper, you mentioned the weather impacts. Obviously, we are talking about wind speed or irradiation and so on. So how do you distinguish between the two, weather and climate? Because this seems to be sometimes interchangeably used.
Yeah, thank you for the great question. And this is something that we have also discussed too. It could be a little bit misleading, but the reason why we put climate change in the title is because climate change affects the weather conditions that are really important for renewable energy generations, especially wind speed and radiation to some extent. So the important factors are radiation and wind speed, but climate change will eventually cause changes in these important elements, wind speed and radiation. So yeah, that's why we
all right. Yeah, I understand. It's typically when we talk about the weather impact, so weather that's more on the short-term basis, and the climate is kind of the slower moving change in the so sometimes it could be confusing maybe for the readers and listeners when you talk about the climate change impact, which I would expect something of a long-term analysis impact on those things, and then at the end, what you're looking at mostly, to my understanding, is more of a weather impact. But that's something maybe you can have a look into again and definitely clarify this in the paper, just not to confuse. Then a second question I had about your decision about the modeling approach using SEM. Could you please a little bit elaborate on that?
So the reason why we chose structure equation modeling was because to look at the indirect effect. in the previous studies, studies look at these direct effects from generation to price, load to price, wind to price. But we wanted to look at the factors affecting these behind them. So to look at these indirect impacts really clearly, because the interaction is really complex, we need to deal with that complexity. And structure equation modeling allow us to deal with this complexity. So that's why we chose SEM.
Okay, yeah, no, this is an interesting approach and allowing you to still work in high frequency or low granularity data, like your hourly analysis. I wanted to have a quick look at the results and the signs of your results. Yes, I was here. Did I interpret correctly? So the direct effect of load, for instance, on prices is positive. There's a positive coefficient, right? But then the temperature, yeah, then the indirect effect of temperature to load, can we interpret that coefficient as well? Is a negative?
So yeah, this part is the only part that needs a little bit of consideration. Other part is intuitively really true and easy to understand, but the effect of temperature to load is significantly negative and statistically significant. And this is because in case of Germany, during the winter season, the increase in temperature could decrease the load more it does to increase the load during the summertime. So yeah, winter and summertime, yep. So maybe in other countries, other region, this could be different.
Yeah,
and that could be another interesting investigation that could be made in future.
Okay. And maybe one more question about when we have these coefficients in front of us, you find a negative relationship between the price and the renewable energy, like solar and wind, confirming the merit order effect. I'm interested especially about the wind. How do you see the possible positive effect also that some studies found on wind and price when we talk about, for instance, the impact of volatile generation? So then we need to dispatch more peakers, more expensive flexible generation. Have you found anything in your study like that, or you just find this direct merit order effect of wind on price?
Sorry, you mean the positive?
Yeah, you find a negative, which is just decreasing directly. So wind has a negative effect on price. But if you think about some situations when more volatile wind generation can actually lead to higher prices because you need to dispatch some flexible, more expensive generation. So it has sometimes a positive effect on price.
For example, during like the suppression and dispatch, that could affect generation of other power plants, which could lead to higher prices.
Yeah.
Yes, definitely. I think that could be the actual situation in some cases, I believe. But in the most of the preceding studies about merit order effect, on average, renewable energy has a negative effect on price, and yeah, which is in line with the theory of merit order effect.
Okay, thank you. I don't know if anybody else has a question. We have maybe time for one question to Alex. Okay. I take the silence as probably no. Nobody's raising their hand. So I would like to thank you, Alex, very much for this interesting presentation.
Thank you very much.
And I think we may continue with our next speaker, who is Theresa.
Hello.
Hello.
Can I start?
Yep, I believe so. If you would like to share your slides.
Yes, of course. Okay.
Right.
Yeah, hello and welcome to my presentation today. I welcome all of you at this, at least for me, quite early time. And I'm going to present our work in progress with the title, The Relevance of Proximity and Workplace Experiences for the Individual Support of Power Plants, an empirical analysis of wind, coal, and nuclear energy. And first, I will start with our motivation. So, like many other countries, Germany is aiming at a more environmentally friendly energy policy. And in order to do so, there are different steps to take in this direction. For example, the expansion of renewable energies. Until 2030, Germany wants to source 65% of their electricity from renewable sources. Additionally, the German government decided on the phase out of nuclear power after the Fukushima accident until 2020, which is already next year. And the last point I want to quickly mention is the phase out of nuclear power that should be done until 2038. And while all these steps are important steps to take in order to make energy policy more environmentally friendly, these steps do not go without problems. And especially the expansion of wind power plants drastically slowed down in Germany in the last years. And this is mainly because of local protests and long approval procedures. Additionally, there are some areas in Germany that are highly economically dependent on coal and nuclear power. And therefore, we can say that it's very important to have the support of the individuals in order to make these changes to feasible policy decisions. Previous studies have already found several factors that influence the support for power plants and their expansion. Among these factors are, for example, environmental values, political identification, age, and gender. And also experience seems to play an important role. And therefore, our study investigates how experiences impact the support for power plant expansion. We look at experiences by taking two kinds of experiences into account. First, the residential proximity to the power plant, and second, the workplace experiences in the energy sector. If we look at residential proximity, there are already several studies that investigate how proximity to wind power plants affects the support levels for wind power plants. In this regard, wind power plants are the by far most studied energy source here. However, regarding coal power plants, there are only a few studies investigating this effect. However, there are some studies that look at proximity to coal on the support for renewable energies. Regarding nuclear power plants, multiple studies look at the effect on perceived risk as dependent variable, which makes sense since the risk of a nuclear accident is an omnipresent risk for people who live in proximity to nuclear power plants. However, there's few literature on the effect of proximity on support levels. If we look at the economic aspects, there are several studies that investigate the impacts of proximate power plants on housing value. And there are also some studies who take the perceived economic impact into account. So for example, the perceived impact on housing value or jobs in the municipality. However, there are only a few studies that directly look at the effect of working in the regarding energy sector. And this is also true for coal and nuclear power plants. And therefore, our study contributes to the existing literature by measuring experience effects for power plant expansions through two components. First, the residential proximity, and second, the workplace experiences. And since these variables are probably correlated, it's important to take both into account in order to disentangle the effects of these variables. Second, we make a systematic comparison of the three most important and politically discussed energy sources, namely wind, coal and nuclear power. And lastly, we consider all relevant variables that have been found to affect the support for power plant expansion in past literature. Now I will get to the data and our variables. So from the literature, we derived two main hypotheses. So hypothesis 1A is about the residential proximity and states that residential proximity to wind, coal and nuclear power plants has a positive effect on the support for the expansion of the corresponding power plants in proximity to participants' residences. And since the results in the literature are not very clear about this effect, we also formulated the hypothesis vice versa, which then states that residential proximity to wind, coal and nuclear power plants has a negative effect on the support levels for the expansion. Our second hypothesis is about the workplace experiences, and we assume from past literature that working experiences in the work, coal and nuclear energy sector have a positive effect on the support for the expansion of the corresponding power plant in proximity to participants' residences. Now I will get to our data. So our data was collected through a large-scale computer-based survey among 3,705 German citizens, and it is stratified in terms of age, gender, place of residence, and religious affiliation. Second, we used the market master data, which is a data set that includes all operating power plants in Germany. And lastly, we used the so-called regional identification register, and I will explain more about that in a minute. So for our dependent variable, we used the following question. To what extent do you support the installation of the following energy power plants in your immediate neighborhood within 2 or 50 kilometers of your residence? And we asked this question for wind, coal and nuclear power. And as you can see here, we asked for the 2-kilometer radius and also for the 50-kilometer radius. And then we derived these 3 main dependent variables, and we decided to take the small radius for wind power plants, since past literature has found that negative externalities of wind power plants mainly arise within a smaller distance around the power plant, while for coal and nuclear power plants, we decided to take the wider distance in order to account for the negative externalities, especially for nuclear power plants that arise in a further distance from the plant. And since these variables are ordered variables, we used ordered probit models for our analysis, and we also derived 3 dummy variables from that and conducted binary probit models. Here you see the descriptive statistics of our dependent variables, and as expected, the support for wind power plants is highest among these 3 energy sources, which is not very surprising. And we also see an incredibly strong opposition of nuclear power plants with 2,800 people roughly that strongly oppose nuclear power plants in their proximity, and coal lies somewhere in between. However, we can still say that there's strong opposition for the expansion of coal power plants in the neighborhood of our participants. Now we will get to our explanatory variables. And since proximate power plants are often associated with negative externalities, we wanted to account for the residential proximity to power plants. And in order to do so, we knew the postcode district of our participants, and we also found out the postcode district of the power plants, and therefore we were able to match our participants with their proximate power plants on this zip code level. And in order to take a further distance into the analysis, we used what I mentioned before, regional identification register. And this register tells us all postcode districts that lie within 50 kilometers of the frontier of the own postcode district. And this way, we were also able to identify these power plants that are further away from our participants' residences. And from that, we derived these three explanatory variables. And it's important to note here that region in the case of wind, again, refers to this smaller distance, while region in the case of coal and nuclear power refers to this wider distance. For accounting for the workplace, we ask the following question. Do you currently or have you in the past worked directly or indirectly, for example, in supplier companies, in the following energy power plants yourself or someone in your environment like friends, family, or colleagues? And from this question, we derived these 3 explanatory variables as we asked the question for wind, coal, and nuclear power plants. Now I will get to our econometric results. So these are our whole econometric results, and don't worry, I will zoom in a minute. I just quickly want to point out that we estimated 2 models for each energy source. So for wind, coal, and nuclear power plants, you see 2 columns. Since we took the proximate power plants as a dummy variable into account, and also we accounted for the number of here, for example, wind power plants in the region. So that's why you see 2 models. And here in the estimation results, you see the discrete and marginal average probability effects of our binary probit model. So now I will quickly look at the results on our control variables, since they are partially in line with previous literature. For example, the new environmental paradigm has been found to have a significant positive effect on the support for wind power plants in the region, while the NEP has a significant negative effect on the support for coal and nuclear power plants in the region. And the same as There we are. And the same effect has been found for the ecological policy identification, while we see the different signs for the conservative policy identification, suggesting that people that identify with conservative policies have a significantly lower probability to support wind power plants in the region, while they have a significant higher probability to support coal and nuclear power plants in the region. Another interesting result is this risk-taking preferences, since we would have assumed that risk-taking has a positive significant impact on the support for nuclear power plants. However, this seems also to be the case for the support of wind power plants and coal power plants in the region. And lastly, I want to point at our effect of age, since we found that age has a significant negative effect on the support for wind power plants, while it has a significant positive effect on the support for nuclear power plants in the region. And as you can see here already, that regarding many variables, the support for coal and nuclear power plants are usually quite similar, while the support for wind power plants is determined by often the opposite effects. So now I will get to our main results. So first, we will look at the proximity effects. And here we see that we have found a significant positive effect of proximity to wind power plants on the support for wind power plants. And this effect has been found for the dummy variable, but also for the number of wind power plants. We also did find this significant positive effect of coal power plants in the region on the support for coal power. However, this effect disappears as soon as we include the German federal state as a regional control variable, and therefore we can say that this effect is not robust against different model specifications. And for nuclear power plants, we did not find a significant effect. And therefore, we can conclude that hypothesis 1A is supported for wind power plants. So for your remembrance, hypothesis 1A was that the proximity to a power plant has a positive effect on the support levels. And we can say that hypothesis 1 cannot be confirmed for coal and nuclear power plants. Now we will get to our results regarding the workplace, and these results draw a very clear picture, since for all 3 energy sources, the workplace experience has a highly significant and positive effect on the support of the regarding energy power plant. And it's also interesting here to look at the size of the effect. So you can already see that the marginal, the discrete change in the probability for coal and nuclear power plants is almost twice as high as it is for wind power plants. And this becomes even more clear if we look at the percentual change. So we have estimated that someone who works in the coal energy industry has a 230% higher probability to support coal power plants in the region compared to someone who does not work in the coal sector, in the coal energy sector. And for wind power plants, this effect is only 100%, while it is even stronger for nuclear power plants. And therefore, we can conclude that hypothesis 2 is supported for wind, coal, and nuclear power plants. And again, hypothesis 2 stated that the workplace experience has a positive effect on the support levels. Now I will get to the discussion and the conclusions. So in summary, we can say that we did not find a significant effect of residential proximity to coal and nuclear power plants on support for their expansion. However, we did find a positive effect of proximity to wind power plants on the expansion, on the support for the expansion of wind. And again, our workplace results draw a very clear picture, suggesting that workplace has a highly significant positive effect on the support levels for the expansion. Now we can come to some conclusions and policy implications. So in total, we can say that the worries about negative externalities from our results seem not to be very reasonable, since people who experience proximate power plants do not seem to have significantly lower support levels than people who do not experience proximate power plants. Additionally, especially our workplace results do imply that we need a structural change in the coal and nuclear energy intensive areas in order to convince local municipalities of the environmentally friendly policies and also to secure the economic basis. Further research could be done to understand the determinants of local support in more depth, and also to compare, for example, the effects of different energy sources with each other. Now I thank you for your attention, and I'm looking forward to your questions.
Thank you, Theresa. That was again very interesting presentation, very topical. And again, maybe I would like you to keep the presentation still open. So if we want to have a look at some of the findings. So as I said, I totally agree that this topic is very, very topical, given that the wind, especially for instance, wind power's expansion is at some countries or regions can reach its limits when it starts hitting the let's say the local residents protests or so its potential cannot be fully utilized for various reasons. Is it the reasons for the permitting processes or the local opposition? So I fully align with your motivation. So the other, like nuclear and coal, still being there, given their phase out in Germany, but still very topical in Germany and elsewhere as well. So the motivation is very clear and
thank you.
Well explained. So I understand you have two main interests. You study the proximity and the workplace experience. So these are also clearly stated in the title. Perhaps I would like to first ask about the work experience dimension. And in your questionnaire, you typically you explicitly state that you have had a direct experience in the field of energy or indirect. Is it possible that we are missing some of the people who might have experience not directly from working in energy field, but from maybe just reading or just from other experiences? Is there a chance that these could be missed in the analysis?
Yeah, that's an interesting question. Thank you for that. So yes, I do think so. So of course we can experience power plants in more ways than just the proximity and the workplace. However, that's the focus of our study, but it is possible that, for example, people who read a lot of newspaper articles about, for example, wind or coal power plants, or watch many documentaries about that, also are influenced by these experiences. That's true, and it's also might be very interesting for future research to maybe look at how knowledge or how much experience people themselves would state they have with the regarding power plants could have. Yes, but we have not considered that, but I do think it could have an influence.
Yeah. And it's possibly anyway reflected in your results, but less directly in a sense. So if somebody says he or she doesn't have an experience in energy, but still they express an opposition or support for something, so it's in there in your results. But I was just thinking whether this could be maybe captured more directly. But no, thank you. That's clear, and it's a most verifiable approach to directly ask about the direct experience rather than just a belief about experience. Yeah. Second question is related to, you had a set of interesting control variables in your model, and obviously there's no time to explain all these, but I saw you had a variable called risk preference or risk taking measure, I think. Could you and you had a finding of I think positive, so do I interpret correctly that more risk taking people would support? Could you explain maybe the definition of this control and the relationship again?
Yeah, so the risk-taking preference was measured through asking the participants for their general willingness to take risk. And it's an audit, so it originally was an audit variable, so they were able to answer it from rather strongly willing to take risk to strongly unwilling to take risk. And we constructed a dummy variable from that. So this variable takes the value 1 if the participant rather or strongly is willing to take risks. Yeah, and again, as you already said correctly, we did found a positive significant effect of risk-taking preferences on the support for wind, coal, and nuclear energy power plants. And yeah, we were also a little bit surprised by that, because we have, as I said, assumed that for nuclear power, since the nuclear risk accident is so omnipresent, but however, it also seems to be true for the other energy sources.
Mm-hmm. Yeah, no, this is definitely interesting, and could be raised in your paper maybe some what is the reason for that, especially exactly like you said with relation to the nuclear power. Maybe I'll just ask one more question here, and we see, or we maybe take the questions at the end. Still 2 more questions, but good we have more questions. I saw that you mentioned it also, the age control and its relationship. So that was also, I think, interesting finding that the negative relationship to support for wind and the age. So there's some age impacts there. That was also interesting, I think.
Yeah. I think this result is also quite in line with previous literature.
Mm-hmm.
Yeah, since usually younger people seem to maybe also be more aware of climate change and environmentally friendly policies, and therefore might be more supportive of supporting the expansion of renewable energies.
Mm-hmm. Okay. And maybe last one, it's a little bit related, but also the experience in the sector had a positive impact on the support. So just think about the policy recommendations. Do you think, for instance, an education of the population in energy topics would help to alleviate some of those opposition?
So I do think education is always a good thing to do. So I do think that it could help, but I also think, especially if we look at these workplace results, then only to educate people that their proximate coal power plant is not very up to date anymore. I think that doesn't resolve the issue that if we phase out coal, there are many people without a job. And therefore, I think it's also very important while educating to give a different and a new perspective to these people. Because I think even if you know that coal power plants are not very good for the environment, if this is your the thing how you earn money, then I think that's a very huge incentive to still support these power plants, even if you know that we should phase out.
Mm-hmm. Mm-hmm. Thank you very much, Theresa. Very interesting discussion and findings. I see that we have a raised hand, Manuel.
Yes, so thank you for your presentation. It was really interesting. So recently I saw a paper analyzing the impact of regional wind power deployment on house prices. So there was a negative impact. And what they as well did is to analyze the installation date of the wind turbines. So what they said basically is that the acclimatization to wind turbines has an effect in time on decreasing housing prices. So after certain years, housing prices grow again. So did you consider to also take a look to the installation dates of wind turbines and how acclimatization to this would affect your results? Thank you.
Yeah, that's a very interesting point. Thank you for the question. So so especially for wind, this whole not in my backyard discussion is obviously a very huge discussion, and this mainly revolves around the construction and planning stage of energy power plant projects. And there are several studies that investigate how the opposition arises during that process, and there are indeed some studies that say that this local protests seems to decrease after a few years of operation. So we did not directly look at that in our study, but there are some studies that do look at the time effects and mostly find that the opposition is mostly arising at the first when the project is proposed, and after a few years of operation, the opposition decreases since, as you said, people just get used to it. This is, for example, also true in the literature for the perceived risk of nuclear power plants. That also just decreases because people just get familiar with this risk. And so what I can say about your question from our results is that, for example, here we did find a positive effect of wind power plants in the region on the support levels. And this would also support the hypothesis that after a few years of operation, the opposition or the local protest decreases. But in our analysis, we only included the power plants that were already installed at the time at which we conducted the questionnaire. So I think that was July 2016. And yeah, and that's when, all wind power plants that were constructed later were taken out of the variables, and we did not directly account for a time effect.
Thank you. I think that was well answered. Do we have any more questions to Theresa? Okay. Seems no. Oh, yeah, we have Lorraine, please. I think we have time for one more question.
Yes, good morning. Thank you for your presentation. I have a question regarding the results about higher education, because in the table you shown, we can see that the effect is negative for wind. And I'm wondering what factors could explain this result, which is a little bit counterintuitive.
Yeah, that's true. So we've also thought about that, so that the high education has a significant negative effect on the support levels. So to be honest, I cannot really explain this to you right now. So we do have to look into this in a little bit more depth. in the future. But you're quite right, this is quite counterintuitive. And so, yeah, right now, to be honest, I don't really have an accurate answer for you.
Okay, I understand. Thank you.
Okay, thank you very much, Theresa. It was an interesting session or presentation and discussion.
Thank you very much.
So we would have the next speaker, Camille.
Can you hear me?
Yes.
Okay, so can you see my screen?
And we can now.
Yeah. I think my video is not working right now.
We can see you, Camille, and we can see also your slides. If you just put them into presentation mode, I think it should be working.
Okay. Thank you so much. So good morning, everybody, and thank you very much for joining the session. So I'm Camille Cany, and I'm working at EDF R&D, and I'm presenting on behalf of collective work with my colleagues, and also in the framework of EU-sysflex European project. So I will first briefly introduce the context of the project and the issue, and then I will go to the methodology and will go also to results and discussion. So as you know, in the European Union, we are on the path of decarbonization by 2050. And this means the transition of the power system with an increasing share of variable renewables like wind and solar. So this transition will be mainly driven by these two variable renewable energy sources, which have priority dispatch, which are non-dispatchable, and which induce some uncertainty in the power system. And so this will have some implication to be evaluated. Right now, in Europe, we have about 30% of renewable energies in the power system. And this is expected to rise by around 50% by 2030, and even higher in the years to come by 2050 and so on. So EU-sysflex is a 4-year project ending this year, and which is gathering many partners, utilities, TSO, DSO, also academics. And the aim is to end up with a roadmap for 2030 for the pan-European power system, where more than 50% of renewables are incorporated in a robust and reliable manner. And this work is part of work package 2, which kind of starting point for the project, aiming at evaluating the challenges, both economic and technical, with increasing shares of variable renewables into the power system. And so here in this framework, we are providing a quantitative assessment and global tendencies on the impact of different shares of variable renewables in the long-term European power mix in terms of installed capacities, operations, and CO2 emission. And in the end, we are looking at revenues and costs for VREs to evaluate the potential needs for subsidies in the long term. So I'll go now to the methodology. Two core scenarios were built and used throughout the European project. They include different installed capacities for the different countries by fuel types, also different demand levels, interconnections, and they are based on the EU reference scenario, which is consensual scenarios from the European Commission. And so we have, in particular, different shares of renewables by 2030 and 2050. 52% in the energy transition scenario, which is composed of 23% of viable renewable energy sources, wind and solar. And for the renewable ambition, we have a higher share of renewable, up to 66%, and 34% of wind and solar in the European power system. And this renewable ambition scenario is the baseline which we use in this present study when we develop various sensitivity around the 34% viable renewable share. So we studied a lower share of 23% wind and solar in line with the energy transition scenario, and two higher shares with 45 and 55% of wind and solar in the European power system, and the sensitivity were done by prorating the wind and solar installed capacity in each of the different countries. And then for each of the variants, the power system was economically adapted so that to reach a target level of 3 hours of loss of load in average per country. And the adaptation was made thanks to gas power plants and peaking units, CCGT and OCGT, and those power plants though are economically adapted, so they cover their costs in the different variants. To do so, we perform simulation with an internally developed European-wide unit commitment model that was complemented with an investment loop. So we have a very detailed data set for the installed capacity, availability, power profiles for the different power plants and per country, as well as interconnection capacities. We have some hypotheses on fuel and CO2 prices, and we model very detailed and many weather years, 55 different historical weather years from the past for the VRE production profiles, as well as the demand profile. And in the electricity demand also includes some flexibility solutions such as water heaters and also EVs, smart electric vehicles, smart charging through tariff signals that are directly included into the demand shape. And so at the first step, we are running the investment loop for each of the variants so that to adapt the power system with the peaking units. And then when the mix is adapted, then we perform the continental model simulation, which comes out with a detailed early dispatch of the different generation and production plan for the different years, as well as projected prices on the market and exchanges between countries. So let's move on to the results now. So one of the first results is linked to the total installed capacity in the European power system. So we can see here the total installed capacity that is increasing a lot with the increase of wind and solar installed capacity. Wind capacity is represented in green here and solar in yellow. And on the other side, so for the different variant from 23% to 55%. And on the other side, you can see a little decrease of the conventional power plant installed capacity. So on the left side of the graph, you have some capacities that are kept ancient, like hydro, biomass, CCS, CHP, and nuclear. And on the middle of the graph, you have a change of the capacity from CCGT represented in red and OCGT in dark here, but the change is quite small compared to the increase of renewables, and it's also shifting to more peaking units, so more OCGT in the power mix when you have more renewable energies in the system. And so this is directly linked to the load factor that are experiencing the different power plants. So you have a decrease of the load factor for the CCGT when increasing the variable renewable energy share because of the form of the residual demand that is gives less room for semi-base load, but more for peaking units. So for a 23% share, you have nearly 60% load factor for CCGT per unit, whereas this is decreasing by less than 20% for 55% viable renewable energy sources. And in the contrary, OCGT load factor is slightly increasing and giving thus more room for these peaking power plants. One other result is about the presence of curtailment in the variable renewable energy sources curtailment in the power system, when their generation is exceeding the demand, including export and storage. So here we can see that for a 23% share, we have nearly no curtailment, but this is increasing up to 10% for a 55% share of viable renewable energy sources. And this, even if in the power mix, we have already some sources of flexibility that are present through interconnection or dispatchable power plants, and even some on the demand side. And here we do not take into account any curtailment coming from congestion in the network. This is only curtailment linked to supply and demand balance. So as an illustration here, we are looking at 2 typical weeks of power production in Germany for the case with 55% wind and solar in the power mix. So on the top of the graph, you have the hourly dispatch. In the middle, you have a marginal cost, and on the bottom, you have import and export. So here we are showing an example of successive low and high wind and solar power production and their implication for the rest of the supply and demand equilibrium. So on the blue rectangle, first blue rectangle, you have quite low wind production, and so the gas power plants have to run with what is shown in orange on the graph. And so this also includes a lot of need for importation for the country, nearly 50 gigawatt at some point, which represent almost half of the demand for Germany, which is quite enormous, and which also implies some high marginal costs during those times. And a few days later, we have, on the contrary, a lot of wind production represented in green here on the graph, and also solar production at midday. And this is implying some curtailment that you can see on the dash yellow here. And so as a consequence, marginal costs are decreasing, of course, and you have some zero marginal cost during time of solar production at midday. And this is to show you another example. So as you know, the mix was adapted to reach 3 hours of loss of load in average per country. So for this example, we show a specific year where loss of load appeared in Germany. And so in this situation, we have not much wind production. We have a lot of gas production to meet the demand. And Germany is importing around 20 gigawatts from the neighboring countries that are not able to export more because of not enough production from other sources like renewables. And so this is leading to some failure hours in the country, and thus marginal costs are sharply increasing as a consequence as well. So now we are moving to some results on economic indicators. And at first, we are looking at the cost structure of the power mix. And we can see here for the different variants, the share between fixed and variable cost, fixed cost being represented in orange and variable cost in blue. So you can see an increase of the share of fixed cost in the power mix. We have like about 60% in the 23% variant, and this is increasing up to 90% for the 55% variant. And this do not also include any substantial additional network costs that were not included in this study, but that could be of high importance for the integration of wind and solar in the future power system. And this is, of course, to be related to the market design issue and to the appropriate schemes that are needed to incentives the right investments in order to reach the decarbonization pathway and to allocate the risk in the appropriate manner. So even not only we have high fixed costs in the power system, but also at the same time some decreasing market prices, as you can see here in average for Germany with the different variant in the orange curve. And this is of course directly directed to linked to the merit order effect. And we have a higher share of hours with zero marginal cost, with increasing wind and solar share in the power system. So now we are looking at revenues and costs for VREs globally in Europe. And at first, on the graph on the left, you have the market value factor, which represent an indication of the revenues for solar, onshore, and offshore wind in comparison to the average market revenue on the system. So in a way, it gives an indication of the benefits of these power sources for the power system, or the value they can bring to the power system. And so you can see that the more you have in the system, the less is the market value factor, and it is decreased in a more pronounced way for solar than for wind, either on or offshore wind. And so this is called what we are calling the cannibalization effect, because the more you have in the variable renewable in the power system, the more their production is correlated, and so the more they will be producing at the same time or not producing at the same time. And solar production is concentrated for a few hours during the day, and so they never can benefit from peak prices during at the beginning of the evening, for example. And so on the right of the graph, you have the average market value that is earned by solar or wind producers. And so this shows accumulated effect of the cannibalization we've just seen on the left graph, and also of the merit order effect with the decrease of the market prices in the market. And so you can see that this decrease even more what the producers could earn in the market. We can see that the average value for the market price for solar is divided by 5, between 55% compared to 23% situation. And for wind, we are a division by 2 or 2.5. And so given the cannibalization and merit order effect, we have impact on the need for subsidies for this technology. So here on the graph, you have for the solid line, the market revenue earned by this technology for the different variants. And on the dashed line, we have some assumptions on projected cost for those technologies coming from the WIO 2018 and for the 2040 new policy scenario. So these are, of course, results in the context of specific assumptions on cost as well on CO2 price. We have a CO2 price of 90 euro per ton here. And so we can see that with this particular assumption, having a share higher than 35% of wind and solar will go further than economic equilibrium, and so the technologies will need some subsidies on the energy only with the energy only market structure. And so this question one more time, the market design and the need for incentives to be able to invest in such technology if the share that we want to put into the system is higher than the optimal economic share for those technologies. And given the cannibalization effect, the optimal share seems to be capped around 35% in the European power system. So now we are coming to the end and summary of findings. So we have seen that renewable energy, and in particular wind and solar, we have a profound effect on the operation of the power system, that they will increase the total installed capacity, but to have a small impact on the decrease of conventional capacities in order to ensure generation adequacy. This conventional capacity will be shifted to more peaking power plants, and the cost structure will also be changing to more fixed cost, while at the same time market value factor and market revenue will be decreasing for variable rest. And if in this situation with a CO2 price of 90 euro per ton, having a viable renewable share higher than 33 or 5%, will need some subsidies to complement energy market revenues. So this opened the question of the market design in order to support the decarbonization pathway. And this was the issue of work page 3 of the European, of the EU-sysflex project. So thank you very much to you all, and we can have the discussion part and question. I will be pleased to answer the questions.
Thank you, Camille. Very, very interesting presentation. Indeed, this is a large project, and maybe if it's fine for you to still keep the slides there, if we want to have a look at some of the findings.
Okay.
So I think we don't have time to go into all the details in this short presentation. But first of all, I wanted to ask about you had a nice explanation about the flexibility sources, the role of OCGTs and CCGTs to provide and ensure the security of supply defined by the loss of load expectations given for 3 hours. So that was very clear, very motivated. I was wondering whether you now have these flexible gas power plants there. Have you considered any other flexible sources providing ensuring the security of supply, such as short-term flexibility sources like batteries, longer-term flexibility sources like power to gas to power, or others?
Yeah. So in this part of the work, we just took into account some basic flexibilities, like a baseline scenario, I would say. So through interconnections, but also some on the demand side, heat water heaters, EV smart charging through tariff signals. And on the task 2.6, here was a specific work to study more flexibility into the power system. So in this work just ended now, and the report will be uploaded and publicly available in a few weeks from now, I think. So task 2.6 of EU-sysflex, here we studied the introduction of stationary batteries and EV smart charging like V1G and with optimal charge and discharge depending on the power system supply and demand, as well as the possibility to make injection into the power system in order to displace the need for OCGT and CCGT. And so we can see that in the simulation, we have like half of the vehicles that are electric vehicle in the transport sector overall in Europe. So it's quite an enormous development of electric vehicle in the system. And they can provide nearly free flexibility and also available. And we have modeled it into details, and we can see that it's displacing, it's decreasing the CO2 price, it's increasing revenues for the VRE, so it's displacing the optimal share to the right, so it allows including more VREs into the power system, and that stationary batteries have their economic place more located in peninsulas like Spain or Italy or Portugal, where interconnection are kind of limited.
Mm-hmm. Okay, yeah, no, thank you. That's interesting, and definitely the CCGTs and OCGT was a good choice, and there was just more. It's a question whether this was considered, and obviously the cost for these will be different, and they will have different if you had let's say seasonal storages, for instance, or short term. Maybe I had another question. It's you presented your model, and it was based on simulation, and then you had, I think, a detailed power dispatch results. So is this a cost minimization kind of type of model, or you're minimizing this power system total costs, or could you a little bit just open that we would understand, just very briefly?
Yeah, this is it's a unit commitment model, so a linear programming where we minimize production cost in the hourly dispatch. Mm-hmm. So this is for the yearly simulation, and to this model we add an investment loop, so it will invest in the technologies that are economically viable, and then run back the unit commitment model so that to check that it's satisfying physical and economic criteria at each time. Mm-hmm. But we do not minimize the investment cost and the production cost. We just minimize the production cost on an hourly time step.
Yeah. Okay.
Yeah.
Thank you. That was clear. You showed a couple of examples from Germany. I was wondering whether you had considered also negative prices in your model, or are they only going to zero?
Oh no, we can't model negative prices right now. So negative prices are zero marginal cost. But of course, we are working on this topic so that to be able to end up with negative prices at the right level, because they are depending on many indicators. So we are internally working on such negative prices as outcome of the model, but here they are not taken into account.
Okay. No, that's clear indeed, because the dynamics of the prices are changing. If we look at the price duration curves, I mean, the volatility and the distribution of those is definitely different in system with lots of VRS or not. But yeah, that's good to know. You definitely thought about that. Yeah, I saw you had another example about the decreasing average prices in Germany. It was an example. So yes, marginal cost drops. I was wondering whether. So indeed, I understand we have more low or zero marginal cost technologies, wind and solar especially, and you see the drop. But do you think if we have in the system some other flexible sources, well, if we had more batteries maybe, or do you think the volatility and the price distributions changes in the system could actually, let's say, offset this decline? I mean, this is the typical argument, yeah. saying decline, but do you think this is necessarily true at all in all situations? This is more just maybe a thought, or.
Yeah, the price distribution will be changing, so we will have higher prices during when VRE are producing. So and low pricing for peaking times. So normally you will have a less important decrease of the expected price on the market, but the price will be more flat throughout the year and throughout the day, so that wind and PV technology will get more revenues from the market, and on the other side, the consumers won't see too much high prices during peak hours. So yeah, a flexibility solution will have the impact of we will see a less decline of the average marginal cost in the power system.
Okay, yeah. Right, yeah. I was also wondering what about this price volatility. So typically we could see also in some systems, let's say, more frequent price spikes, and that could maybe push the average prices as well a little bit higher. But yeah, that's just a comment to explore maybe. Yeah, I see there are two raised hands, so maybe I'll stop here and give floor to the audience, please. I think Clement was first, if I'm not mistaken.
Yeah, I don't know, but
okay, please.
Okay, thank you. I have two questions. So first, I was wondering whether or not you try to test this model on historic data, like to confront we'll see how the simulation works, where on situations like the past years, and whether there is some discrepancies between what really happened in terms of price, in terms of dispatch, and what the model would have predicted. Like, could you see some like patterns in bias in the model simulations. And my other questions was regarding the drops in renewable revenues. So you mentioned due to the cannibalization effect, then offshore wind and solar revenues will drop consistently from now, I understand. So why does this account for the fact that costs, wind and solar costs are still decreasing? And did you try to question whether when will the cannibalization effect become bigger than the cost decrease effect for this renewable?
Okay. So for the first question, so the model is a very detailed model, and in particular, we are modeling 55 historical weather years for the different VRE profiles that are constructed thanks to radiation, wind, and in the different locations, and also for the demand. And we are taking the same weather year for both data, so that the data set is coherent. And we are using the model internally or as a routinely. And so it's I would say the way we're using to test that model is good at predicting the future with different variable renewables. So we have internal studies on that. And when it comes to your second question, this is maybe the answer. So we can see that the cannibalization effect is very important, and it's overpass the effect of cost reduction in the power system with high share of variable renewables, like 45 or 55% by the time horizon of 2050 or so. And so, of course, these results are sensitive to cost assumptions and so on. But we can see that the cannibalization effect has the strongest effect on the dynamics of revenues versus cost linked to the deployment of solar and wind energies.
Okay, thank you very much.
Thank you.
Thank you. And we have time for one more question by Laureen, please.
Yes, thank you. I just have a question regarding your hypothesis for interconnection capacity. Have you considered the current capacity, or have you introduced some expansions?
Yeah, so we have introduced a lot of expansions. And to be honest, the scenario is quite optimistic here. We are the assumptions are not detailed in this presentation, but they are detailed in the paper. We are in the detailed paper. So assumptions on hypotheses are coming from the EIWay scenarios, and we have in total for Europe 300 gigawatt of interconnection. This is 3 times higher than what we have today. So it's very optimistic on our viewpoint. And so in the study with the different flexibility analysis, we have studied a variant with less interconnection than in this baseline scenario, like to see the influence of interconnection also in the different indicators to better integrate solar and wind.
Okay, thank you.
Thank you for your questions. Maybe as a last comment or forward-looking comment. So when we see these cannibalization effects and kind of missing money from the energy-only market, and you mentioned that this has been explored in other work stream of your project, but have you found out any solution to the energy-only market design question when you show your results?
Yeah, that's a good question. Actually didn't work for this work package 3, but the results are online. So maybe I would rather suggest to read than to go and see on the website of the project, because I'm not the right person to answer to you on these market design options.
All right, no problem. Thank you. So if there are no more questions from the audience,